PA5 has two main parts. The first part is loopy belief propagation algorithm. The second part is MCMC sampling techniques. This video I'm going to talk about the first part, which is loopy belief propagation. The best place to start this assignment is this rewritten PDF by our fellow TAs. They have actually done a wonderful job of writing this. They have clarified a lot. They've given a lot of helpful hints across the board. So this is the place to start your PA5 assignment. This assignment is slightly hard compared to others, but I hope with this rewritten document by the fellow TAs, hopefully this will make it easy. So the first part, which is loopy belief propagation algorithm, it has some few subparts. You have to implement the naive get next clusters, create cluster graph, check convergence, cluster graph, calibrate, and compute approximate marginal BP. So the first one here, naive get next clusters, it takes two arguments, P, M, and then returns I and J. So let's investigate what these are. So I've already loaded the example IOPA. So if we look at who, so we take this, and there's a slight convention, but I think you'll get used to it if you play around with it. I'll actually show it to you. So because this is the first one, so they're calling this as so you say example input test 1 argument 1, which will be this P. So let's say P equals that, and then let's see what this is. This P is same as the one that we've been doing in PA4. Instead of click list, we're just calling that now a cluster list, and then you have edges here. So the next one is M. So M equals actually let's see what this is. So if I actually, so argument 2, so T test 1 argument 2, that is A2. So if I just do that, you see how they've given you cell array, and it has 3 sample inputs that you can use. So if we can take one of those, for example, like the M equals example input dot test 1 argument 2. We want to use the first sample, for example, let's say so, or we could have used even the last one, so like that. So what is this M? This M is the number of messages that have been passed so far. So if M is 0, that means 0 messages have been passed so far. If M is 5, that means 5 messages have been passed so far. So note that this M is an integer, it's not some message data structure. So just like this here, it's just some number. So it basically tells the number of messages that have been passed so far. So what is it that you have to do in this assignment? Well, given this number of messages that have been passed, for example, let's say M is 5, you need to compute what is the from index I and the, that is this I, and the destination index J for this 6th message. So if M is 5, you're computing for, so if 5 is passed, so you're basically computing for the 6th message what is the from index I and the to index J. If M is 0, that means you're computing, okay, the next message is 1. So for the first message, what is the from index and what is the to index? That's what you need to compute. Obviously, the other thing here they're saying is, if M is 0, Ij will be the pair of clusters with lowest J value. So make sure you take note of that. In my case, I was using for loops here, and so I started with J as my for J equals and then for I equals. So the next thing, and very important thing in this subpart, is note that this M, because you keep passing messages, obviously this can be way more than the sum of edges you have here, right? So you need to make sure you use mod function to cycle that M whenever it goes beyond that, and total number of edges. Okay, so that's the most important thing to keep in mind. The next one is create cluster graph. Well, this is actually what you have to do really in this assignment. You're basically given a set of factors, and all you need to do is just like how it's explained in the lecture in the beta cluster graph. So you have to basically, using those factors that they gave you here, you have to create this beta cluster graph. So what is this beta cluster graph? So on one side here you have singleton clusters, meaning each cluster has one variable. So like in 6 has A, 7 has B, 8 has C, and so on. On the other side you have all these other clusters with more than one variable, and the goal here is like here, so this has got A here, and then you go and look, okay, where else you have A on this other side? Well, on this one there's a, so you connect them with this edge. And you note that there's nowhere else you see A, so you don't, so you only have one connection here. Then, okay, you look here. Okay, here is B. Where else do you have B here on the other side? Well, you have B here, so there is an edge from 7 to 1. You have B here, so you have an edge from 7 to 2. You have B here, so you have an edge from 7 to 3, and so on. So really, the most of the programming part is basically, as you basically need to set these edges properly, so that it's a beta cluster. As you've learned, beta cluster is the simplest way to create a cluster graph. The next part in this assignment is check convergence, and then you have cluster graph calibrate. I'll come to check convergence here in a minute, but let's go and see what this cluster graph calibrate, what you need to do. So again, this is pretty much similar to click tree calibrate that you've done, pretty much identical with few exceptions here and there. So the first thing you have to do in this code is to initialize. So so basically P is pass, right? Basically for this, I mean, you can just assume that use smart will be 0 for this programming assignment, but I highly encourage play around by passing 0 and 1. So here what you have to do is, you see how we have these messages, right? They're initializing, so if you go through this you'll understand. Pay attention to how these things are created. And so again, as usual, you can use, for example, for test, this is what 1 2 3 4th test, right? So if you want the input P here, you'll do the same thing, right? So example input test 4th one, so it's T4 argument 1, so like that. Okay, so same thing. And then the most important thing, see how they're creating this messages here, and then you have to initialize this properly. You have to initialize properly the cardinality, you have to initialize the where and the vals. Initialize the vals to 1, so that's the most important thing. So now actually we can briefly also go and look at the belief propagation algorithm here. See how they said initialize all messages to 1, so keep that in mind. The next thing is basically here the computation of message is identical to what you have done in the PA4 assignment. Basically what you're doing is, so the way you compute message I to j is, you take all the incoming messages to node I and then you do a factor product on them, and then you again multiply with the psi I, which is the p dot cluster of I, and then you sum over. Basically you would use set diff to find out the variables to sum over. So actually if you excuse me, so if you scroll down here, this is where you would be implementing all that stuff. So you would find out the variables to sum out, then using set diff, then what you would do is get all incoming messages to I except j. Once you get those, then you use factor product to multiply those. Basically you would perform factor product on those messages, and also make sure you factor product with the p dot cluster list of I, which is your psi. Then obviously you would do factor marginalization over the variables to sum out that you calculated, and normalize, and you update the message. It's pretty much exactly like how we would do in your PA4 assignment. And then you, if you look at this, this is like a while loop. So how does this while loop, how does it break? So well, just like the in the lecture slides, um, I think it was right here, repeat until when. Well, so they have given you this little function which is check convergence. If you study this code, you are actually saving these current messages and the previous set of messages, and you pass that to this check convergence function. And basically here what you have to do is uh, converge, so that you return, so you pass the new messages and the old messages. Converge should be 1 if converged, otherwise it should return 0. Okay, and basically you will find absolute and find functions useful here. And last thing, here is compute approximate marginals BP. Again, this is if you notice, again you're using, you know, the things that you've done, basically create cluster graph calibrate, and then basically here again it is pretty much identical to compute exact marginals BP that you did in PA4. So you can pretty much reuse that here. The only thing you need to keep in mind is you're also passing evidence here. One last thing that I want to mention is regarding the output. So for example, if you have like the first function, right? So if you want to calculate, if you want to see what the output is, you would just say example output, right? Output. You know, the first one returns I and j, so let's equals, and then see what it does. Test 4 example output dot, sorry, we are looking at, let's look at T1. So that's that. T1, I'm doing something wrong here. Example output dot test 1. Okay, yeah, so that's how you would do that. So you get the example outputs. For T2, same thing. Now obviously for T1, remember you can pass more than one message, so I believe so you have to use cell array to do that. Now one most important thing, which is really what I want to show us, if you do like T4, you may get error. And so the convention, if you have more than one output here, like for example here in so you're what are we, if you look here, we're returning PN messages, for example, right? So you would say O1 and then O2 for those messages. Okay, so O1 will give me that P and O2 will give me that messages, which is slightly like and if you want to do T1, I think for the first part, you do something like that, and then you would use seller. So just some you'll get used to it, but I especially for the T4 I remember struggling, and I want to make sure I show that to you. Good luck and thank you.